So a discrete random variable is a variable which takes on a countable number of distinct values. And a situation where we might get distinct values could be when we roll a six-sided die. So we could either get a 1, a 2, a 3, a 4, a 5, or a 6 in that particular experiment. And there might be another situation where maybe we flip a coin and we actually count the number of times that we get a head or a tail. So you could flip this coin multiple times and count up the number of tails that you get. These would be modeled by discrete random variables. And our discrete random variables, they're often represented here with a capital letter. Most of the time it's with a capital X, sometimes a Y. It doesn't matter, you can choose whatever letter you like, but often it's with an X. So if we look at our rolling of a die, if we were to roll the number 1, then our X would be equal to 1. If we rolled a number 2, then X would be equal to 2. Likewise, if we flipped a coin multiple times, let's say we flipped a coin 3 times and we wanted to count how many tails we got, and we got 3 tails out of those 3 coin flips, then X would be equal to 3. Now we're going to dive into these 2 examples particularly, and one more through this video. So the first example looks at our die. So here we're rolling a fair 6-sided die, and we denote the random variable x to represent the number which is rolled. For example, the probability that x is equal to 1. Well, our random variable x here is modeling, or it's representing, the number which we roll. So this is just like saying, well, what's the probability that we roll a 1? And on a 6-sided die, that's just 1 out of 6. Likewise, we could say the probability that our discrete random variable is equal to 5. Well, that's like saying, what's the probability that the number that we roll is a 5? And again, this would also be 1 out of 6. In fact, we can determine the probabilities for every single possible x value, and we would represent this in what we call a probability distribution table. So a probability distribution table, and we'll draw one down here, so probability distribution table. What these look like is they are 2 rows. This one up here has a little x, and this bit down here is the probability that my discrete random variable is equal to this little x. And I'll get to that notation in just a moment. But what we have here is we have all of our possible outcomes that we can get. So on a die, we could get a 1, a 2, a 3, a 4, a 5, or a 6. Now, exactly what's being said here is that we are down the bottom here in the second row, we are saying what is the probability that my discrete random variable, or in this particular case the number that I roll, is equal to the little x, whatever number is represented in the top row. So for example, in this box, we're saying what's the probability that I roll a 1? In this box, what's the probability that I roll a 2? All the way down to the final box where we're saying what's the probability that I roll a 6? And well, for a die, we know that all the numbers are equally likely to show up. So it's a 1 out of 6 chance in each particular outcome. Now, that's not always the case for every discrete random variable distribution. Some experiments will have different probabilities for different outcomes, but for this particular case of rolling a die, they all have the same outcome. In fact, we can call this thing a probability density function, and that's for 2 reasons. So for a probability density function, or a PDF, there are 2 criteria to be met. The first criteria is that there's no negative probability. So for example, the probability that I roll a 6 can't be negative. Even if I was to put the probability that I roll a 7 in. Well, the probability of getting a 7 on a 6-sided die is just 0. But that's not negative. So the first rule is we can have no negative probability. The second rule is that all of the probabilities must add to 1. So if you add all of our probabilities here, if we add all of our 1/6 together, we've got 6 of them. So all of our probabilities add to 1. And that's really important because we've got to make sure that in our probability distribution table, we have all of the possible outcomes. If these numbers didn't add to 1, then we would be missing a potential outcome. So they're the 2 criteria for a probability density function. Now we have to look at a couple of things that we can do with this probability distribution table. So let's come down a little bit, give ourselves a touch of room. There's a few sort of properties that we can get. One of them is what we call the expected value of our discrete random variable, and that's given by this shorthand notation E of x. And that's also called the mean, which is denoted by this little Greek letter mu. And the way that we calculate that is we take the sum of all of our x values multiplied by the probability that they occur. So you'll see what this means in just a moment, and it's not too tricky. So we take our first x value, which is a 1 here. So we take our 1 and we multiply that number 1 by the probability that the 1 occurs, so 1/6. Add the next one, 2, multiplied by the probability that that occurs. Add the next one, 3, multiplied by the probability that that occurs. All the way down to my number 6, multiplied by the probability that the 6 occurs. And if you were to do this sum and you were to add all of these up, your expected value, or your mean in this particular case, would be 3.5. And that's what we expect. We would expect this to sit directly in the middle of between 1 and 6. So 3.5 would be your expected outcome for your discrete random variable. The next thing we can do is we can calculate what we call the variance of x. And we give this the symbol little sigma squared. Okay, and the way that we calculate that is very similar. We take the sum of x, but now we subtract from x the average, so our mu, which we just calculated to be 3.5. We square it and we multiply by the probability that x occurs. Again, this looks quite scary, but in practice, it's okay. It's a little bit more tedious than the mean, but it's still doable. So we take our first one, our number 1. We subtract from it 3.5, and then we square it, and then we multiply it by 1/6. We then add on, go to our number 2. We subtract our mean of 3.5, we square it, and we multiply it by 1/6. We continue this process all the way down until we do the last one, my number 6, where I subtract my mean, 3.5, I square it, and I multiply it by its probability, which is also a 1/6. And again, if you were to put all of this into a calculator, you would end up with the number 2.917 as a measure for the variance. Now, the variance is just a measure of the spread of the data. And a lot of the time, we sometimes, to measure the spread, instead use what we call the standard deviation. And this is just given by little sigma, which means that if you compare sigma squared to little sigma, all we have to do to get the standard deviation is take the square root of the variance. So if you took the square root of 2.917, you would get 1.7079. And that's how we can calculate the expected value, the variance, and the standard deviation of our discrete random variable based off of our probability distribution table. A couple of extra little points that I want to make around the probability distribution table is just some of the notation when you might be asked some questions. So you might get asked to find the probability that x is equal to 2. Well, we did those okay at the start, and we just look at in the 2 column, and we see that that is a 1/6. What if we were to ask the probability that x is greater than 2? Well, now we're looking in any of this space. So you would be looking at 4. So you could get the probability that x is a 3, for example, plus the probability that x is a 4, plus the probability that x is a 5, plus the probability that x is a 6. So that would be how we would calculate the probability that x is greater than 2. So we're looking in this section of our probability distribution table now. And in this particular case, that's just 4/6, or 2 out of 3. A couple of other points that I want to make is, what if we were to ask to find the probability that x was less than or equal to 1? Well, then that is just the probability that x is equal to 1, because we don't have anything lower than 1. So in this particular case, again, that's just 1 out of 6. So that's just this column here. But if we were now to ask to work out the probability that x is greater than 1, Well, you could add up all of these if you wanted to, or we could just do 1 minus the probability that x is less than or equal to 1, because of the rule that all of our probabilities must add to 1 in total. So one takeaway, the bit highlighted in yellow here, if we did 1 minus a sixth, we would end up with all of our potential outcomes in this space. So our answer to this question would just be 1 minus a sixth, which is 5 out of 6. So hopefully that's made some sense. We're going to have a look at a couple more examples, okay, at some different types of questions that you might get. And these ones aren't going to have a consistent probability, which is always equal to a sixth or always equal to the same thing amongst all of the potential outcomes. So if we come over to example 2, we flip a fair coin twice and we let the discrete random variable x denote the number of tails obtained. So before we start to think about this question, we need to work out what our sample space is. So if we flip a coin twice, we could get a head and then a tail. We could get a head and then a head. We could get a tail and then a head, or we could get a tail and then a tail. And each of these have equally likely probabilities of happening. So the probability of this happening would be 1 in 4, and this one also 1 in 4, and likewise for the rest of them. They're all equally likely to occur. But notice the question says, let the random variable x denote the number of tails that are obtained. So if we look at our first example, so this one here, if we got a head then a tail, then x would be 1 because we've obtained 1 tail. Here we got no tails, so x would be 0. Here we got a tail and then a head, so we got 1 tail, so x would be 1. And here, both tails, x would be 2. So if I'm going to create the probability distribution table for this, I would have my x and then my probability that my discrete random variable is equal to whatever I pop up here. And I've got 3 possibilities. I can get no tails, I can get 1 tail, or I can get 2 tails. And so the probability that I get no tails, well, that's only this one here, so just 1 in 4. The probability that I get 1 tail, well, I've got this one up the top here, or this one here, so that would be 2 out of 4. And the final one, the probability that I get 2 tails, that is also 1 out of 4. And we can check that this is a probability density function, because if we add all of our probabilities together, we get 1. So a quarter plus 2 quarters plus 1 quarter is equal to 1. And there are no negative probabilities. So this is most definitely a probability density function. Now, let's say that I was asked to work out the probability that x is greater than 1. Well, the only option that allows x to be greater than 1 is when x is equal to 2. So that would be 1 quarter. Now I could also try and work out the probability that x is less than or equal to 1. Now I could do this one of 2 ways. I could work out the probability that x is 0 and add that to the probability that x is 1. So I would end up with a quarter plus 2 quarters, which is just 3 quarters. Or I could say the probability that x being less than or equal to 1 is just 1 minus the probability that x is greater than 1, which we worked out to be here, which is a quarter. So here we're using the complement. Okay, so there's one of 2 ways that you can do that. And whichever way you choose to think about it or whichever way you find easiest is okay. But it's good to have an understanding of both for different types of questions. Now, let's take our probability distribution table and let's work out what the expected value of x would be. So remember, that's just the mean. And the way we calculate that is just the sum of x times the probability of x. So we do 0 times a quarter. So we get 0 times a quarter, and we add that onto the next one. So 1 times 2 quarters. And add that onto the next one. So 2 times 1 quarter. And if you were to do that in a calculator, you would just end up with a half. So the expected number you would just end up with 1. So the expected number of tails that we should... So the expected number of tails that we would expect to get when we flip a coin twice would be 1 tail. And that kind of makes sense. If we try to calculate the variance of x, remember that's just sigma squared, which is denoted by the sum of, and we'll zoom this out a bit and give ourselves some room, x minus the average squared times the probability of x. So we do our 0 minus 1 squared, and then we multiply that by the probability of getting 0, so that would be a quarter. Add that on to 1 minus our mean squared, multiplied by the probability of getting a 1, add 2 minus our mean squared times the probability of getting a 2. And if you put this into a calculator, you just end up with a half. Now finally, the standard deviation of x, which is just given by sigma, is just the square root of the variance, and that is just the square root of a half, which is 1 over root 2, and if you pop that into a calculator, you get 0.7071. And if you think that number looks familiar, it does, because this is an exact value for the sine of 60 degrees or the cosine of 30 degrees, which is totally unrelated, but it's funny how these numbers pop up. Finally, we will have a look at a last example. So here we've got 7 balls in a bucket numbered 2, 4, 5, 6, 9, 11, and 13. And we pick 2 balls out from the bag and we note their numbers. So here notice we're not replacing the balls, and that's going to be really important when it comes to calculating our sample space and things like that. Let the discrete random variable, x, denote the number of prime numbers drawn from the bag. So we're looking for the number of prime numbers that we draw from the bag. So let's circle our prime numbers. So that would be the number 2, the number 5, the number 11, and the number 13. There are all prime numbers. So what we could do is, remember, we're picking 2 balls out. So x could be 0. We could get no prime balls. We could get 1 prime ball, or we could get 2 prime balls. Now, if we're going to get no prime balls, the only way that that can happen is if we get a composite, and then, on the first go, and then we get another composite. Okay, so the probability of getting a composite on the first turn would be, well, there's 3 composite numbers there, so 3 out of 7. And then on the second turn, well, there's only 2 of them left, so 2 out of 6. And if you multiply those together, you just get 1 out of 7 as a simplified fraction. Now, we'll leave the when x is 1, and we'll come over to us getting 2 prime numbers. Now, to get 2 prime numbers, we have to get a prime, and then the second time we have to get a prime. So to get the first prime, that would be, well, we've got 4 prime numbers out of 7, and the second prime, well, we've got 3 left out of now only 6 balls, because we're not putting that ball back. So that changes things. It's really important to think about. So if we simplify that fraction down, we just get 2 7s. Now, when x is 1, we've got 2 possibilities. We could get a composite and then a prime, or we could get a prime and then a composite. So 2 different ways to do that. It's kind of like how you can get a head and a tail, or you could get a tail and then a head. So we kind of saw that in the last example. Now, to go composite then prime, I would need to go 3 out of 7, and then, well, I've still got the 4 prime balls out of a possible 6. And that, as a simplified fraction, is just 2 7ths. And then to go prime then composite, well, I need to get the prime number first, so 4 out of 7, multiplied by then the composite number, so 3 out of a remaining 6, which is also 2 7ths. So my total for x is 1 would be 4 7ths, so I could add those 2 together. So if I completed a probability distribution table, and I might do it over here, I've got x and then the probability that x is equal to x, I could get 0 primes, 1 prime, or 2 primes, And they have these probabilities respectively, which we calculated. What can we do with this? Well, we could calculate the expected value, the variance, and the standard deviation for this. So if we take this probability distribution table and we were asked to find the expected value of x, well, this is our average, and that's the sum of all of our x's multiplied by the probability that occurs. So we would have 0 times 1/7 plus 1 times 4/7 plus 2 times 2/7. And if you put all of that into a calculator, you just get 1.14. So it's not a whole number this time. So the expected number of prime balls that we would expect when we pull 2 balls out the bag would be 1.14. So that's over a long period of time. Of course, we can't get 1.14 of a prime ball on a singular trial. This is an average, a weighted average over time. Now, if I want to find the variance of x, that's just my sigma squared, which is the sum of, remember, my x minus my average squared times the probability of x. So I would put my 0 minus my average, which is 1.14. I would square that, and then I'd multiply that by the probability of getting a 0, which is a 1/7. If I zoom out a little bit more, I can add on. I'd do 1 minus my average squared times the probability of getting a 1. Add on 2 minus the average squared times the probability of getting a 2. And if we put all of that into a calculator, we just end up with 0.4082. And remember, that's just a measurement for the spread of the data. And a lot more often, we tend to use the standard deviation, which is just the square root of the variance when we're talking about the spread of data. And if you pop that into a calculator, so you take the square root of 0.4082, and you would just get 0.6389.